Okay, so this is the last video covering what we call 1.1, which is basically a multi-step equation review from Algebra 1. So nothing new here. This is all things that you've encountered in previous math courses, likely. But if you're looking at this for the first time, hopefully this helps you. And even if you're not looking at it for the first time and you just plain forgot it, hey man, that's cool. I get it. All right. So here we go. So this is these two are going to give us interesting results, and you'll see in a second, right? But we're also going to incorporate bits and pieces of what we talked about in the other videos. So we're going to talk about distribution. Well, we'll do distribution, and then we'll have to do some rearranging and choosing sides where we're going to put things and stuff. And you'll see in a second kind of what happens. All right, so let's start on this first one. So I got negative 2x plus 9 equals 2 times the quantity 7 minus x. So the very first thing, if we think about our order of operations, let me change my line. Oh, it is. All right, good. We're going to use PEMDAS, right? So parentheses always come first. So let's deal with this guy, right? And 2 times 7 is going to give me 14. And 2 times negative x gives me negative 2x, right? And then this side over here is negative 2x plus 9. And then now we are at a situation where we go, okay, we need to kind of move the variables to one side and move the numbers to the other side, right? Because we have a balanced equation here. Whatever you do, you got to do the same thing to the other side. So we got a curious situation, because normally what I tell people is, hey, pick a side for the variable. Pick a side for the variable that already has more of it than the other. That's the side you want to pick. The problem with this one is they're the same. All right, so it's kind of like, so you can pick either one, right? So let's move variables to the left, because that's kind of traditionally how we like looking at these things. So that means that this guy right here needs to go over here. So we are going to do that. We're going to add 2x to this side, right? So we're highlighting this one, right? And so because we're highlighting this one, we're going to get rid of it and do plus 2x to get rid of it. And then we're going to add 2x also over here. Now, what happens as a result of this is what makes this a special case, okay, is that you get these cancel. These are supposed to cancel, but these cancel in the process as well, right? So we get nothing. We have no x's. So we wind up with 9 equals 14, right? And now the thing is, you know that we have to have a balanced equation. Well, if you have anything that says 9 equals 14, that's not balanced, right? Because 9 is not as large as 14. In order for this to be balanced, you would have to have something where they were equal to each other, and these are clearly not equal to each other. And so when you get that case, that is a case where there is no solution. That means that there is no x value that you can put in for where the x's are in the equation that is going to satisfy this and make this come true. There's nothing. So you just go no solution. And there's there's other ways of calling this no solution, but I think no solution is the easiest route to go here, because it makes sense. There's no solution, doesn't work. All right. So generally speaking, when you have a situation where your variables get cleared off when you move them, you're going to have either this or what you're going to see in this next problem. All right. So you're going to have one of two cases. So this is case 1. Okay, we'll just call it case 1, and we'll use the Roman lowercase 1 there, I. Okay. So now let's do this one. So again, following PEMDAS, right? We're going to do our parentheses first. So we're going to do u and u. So let's bring this down a little further this time. So we get 3 times x, which is 3x, And then we get 3 times 2, which is positive 6, because positive 3. Okay, now over here we get, I'll just write this out, x plus 9 plus 2x minus 3. So hopefully you see now the next thing we're going to have to do is some collection, right, on the left side. The right side's just got 2 terms, so we're good. But we got an x here, we've got an x here. Notice that when I'm talking about collection, I'm always including the sign to the left of it, right, even if I'm doing it sloppily because of this pad, but that's how it works. All right, x plus 2x gives me 3x, all right? And then, here, let me make that look a little more legible. 3x, and then my numbers, my constants, 9 minus 3 gives me positive 6, okay? And then that equals what we have over here, which is 3x plus 6. And if you're noticing something here, this side is exactly the same as this side. Okay, so I think it's going to be pretty clear what's going to happen here, right? But let's just finish it off. Let's see this through to the end. So again, let's move the variables over to the left side. So we go negative 3x, right? So that gives you a cancellation of the variable here and leaves x. And on this side, it does the same thing. It cancels the variable, and it also leaves, or sorry, it doesn't leave x, it leaves 6, right? And it also cancels the variable over here and leaves 6. So now we have this thing that says 6 equals 6. Well, this is always true. This is always true. This is what we call an identity, right? And so when you have an identity, the way we interpret that as a solution is that pretty much what this is saying is that no matter what you put in, it will always work. You can put any real number in this, and it will work. So your solution to this, you could say, you know, x is all real numbers, right? That's one way of calling it. Say x equals all real numbers. You could say x equals like that. You could also say infinite number of solutions, because if x is all real numbers, the number of real numbers there is infinite, right? So it means, so these all kind of mean the same thing. They'll all signify to whoever is looking at this that you understand that everything works for this. So those are your 2 cases. Now, the thing I want you to get from this, right, from on this problem, is when you get to this step right here. So when you get to this step right here, okay, so that's this one right here, I want you to hopefully be able to see before you do all this, right? Not that it takes that much time, but save yourself a little time. Hopefully you'll see when you get to this step right here that, wait a minute, both sides are completely equal to each other. So at this point, you can recognize your identity. And when you recognize that you have an identity, in other words, the left side is completely the same as the right side. They're mirror images of or not even mirror images of each other. It's like you cut and paste it, right? So when that happens, then recognize that that is where you have an infinite number of solutions. All real numbers work, right? And then you can stop and just show that, right? Write that down. And then that should be enough work to satisfy anybody unless they want you to force it through. But that's how it works. These are your 2 special cases, right? I'll just for closure, we'll write that this is case 2, all right? So thanks for watching, and we'll see you in the next set of videos.